Interest. So folks, welcome to our meeting. Just a couple of things on security and Zoom. We are in webinar format, which is fairly secure. However, some people may post nefarious links in the chat or question and answer windows. So please do not click on any links that are within the chat or Q&A windows. If you have a question for the presenters or a question for any of the panelists, please use the Q&A box. The chat box is just for you folks to chat among yourselves. We will not be monitoring that throughout this evening. So tonight's program, we've got, sorry, the title for Cass Marion has changed. Sorry about that. Cass is going to be talking about some training she's done with astronauts on the moon exploration, and we'll cover that off. Sorry, this was a preliminary title that was on here. So you're getting my very rough introduction for myself right now. We're going to do the Ottawa Skies, and I'm really pleased to have Dr. Cassandra Marion, who's the science advisor for Canadian Aviation and Space Museum, speak to us this evening. We're going to have a break with our Messier and Moon Challenge. We're going to have our observations and announcements. Okay, moving on. So we welcome new members to the RASC, and our guest speaker this evening is a new member to the RASC, so welcome, Cass. We have 52 members so far in 2021. We do have some members in the news. This was really cool. Pierre Montin's picture of the Perseid meteor showers made it into NASA's astronomy picture of the day. That's a really big thing. There's only 365 of these pictures a year, and his was selected. Was last week on the 24th of September. So congratulations to Pierre. And congratulations to Andrea, who has got her Deep Sky Astro Imaging certificate. It was presented on the 24th of July. And here are some of her images. Great job, Andrea. Okay, so let's take a look at the Ottawa Skies. What's happening in October this year? Well, we've got the phases of the moon. We've got the new moon on the 6th of October, and the full moon is on October the 20th. This full moon was known by early Native American tribes as the hunter's moon, because at this time of the year, the leaves are falling and game is fat and ready to hunt. The moon has also been known as the travel moon and the blood moon. We've got two comets that are up there right now that I have information for. One of them is Comet 29P Schwarzmann-Walkman, and this is the path for this comet. These images will be an astronaut, so it's a bit of an eye test right now, but they will be published in Astronauts, so you can take a look, and this gives you the position of that particular comet. And then the other one is Comet Atlas. And I've got the positioning of that up until October the 11th on the screen here. We have the Draconids meteor shower. It's a relatively minor meteor shower, about 10 meteors per hour. But this month, it's just a day or two after the new moon, so it'd be excellent viewing opportunities if and when they do appear. They run from October 6th to the 10th. And peak on the night of the October 7th and 8th, overnight there. So best times probably after midnight, and it'll be nice dark skies. We have the Orionid's meteor shower, and it's a little more robust meteor shower, but unfortunately, it's 2 days after the full moon, so it's going to be very difficult to see the meteors, about 20 meteors per hour. These are remnants from the dust from Halley's Comet. And then I got one more meteor shower. This is next month, but it happens the day before our next meeting. So we have got the Northern Taurus meteor shower, and it's best viewed after midnight. A moon won't be too much of a problem then. And so that is the November 4th and 5th. And it's only about 5 to 10 meters per hour. So it's a fairly minor meteor shower. As you can see from here, the days are getting shorter and shorter, which means that we can start our astronomy stuff earlier in the evening, which is great. Mercury, on October the 25th, Mercury be the greatest western elongation. So just before sunrise, Mercury will rise before the sun, and it's one of the better times to see Mercury on October the 25th. Venus is visible in the evening, and October the 29th, we have the greatest eastern elongation, and look in the western sky just after sunset. And Mars is not visible. It's basically rising and setting with the sun right now. Jupiter is visible in the evening, as is Saturn. Uranus is visible in the evening and through the night, as is Neptune at this point in time. And there is our cartoon of the month, or our picture of the month, I guess. I was pretty close. That meter just missed the visitor center. Okay. Now, I'm still offering a virtual interactive introduction to astronomy for beavers and sparks and for Cubs and Scouts. I've also done it for seniors groups as well and regular adults. You can always email me if you're interested in me doing this. It's about an hour and 15 for the older groups, 45 minutes for the younger groups. I haven't started in-person sessions yet. I'm hoping to do that later on this fall. And then there's a follow-up to the longer program called Astronomy, the Next Presentation. And again, if you're interested, please contact me, meetingchair@ottawa.rasc.ca. So here is the correct title for Cassandra's talk. I apologize for that. So she's going to be talking about Mistaston Lake and an expedition she was involved in to prepare the astronauts for field geology in the moon. So for those of you who don't know Cassandra, she is the new science advisor for the Canadian Aviation and Space Museum. Well, I say new, but she actually started last November. She replaced Jesse, who we knew from before. And she has her PhD from Western University in planetary geology. And I'm really pleased to have her here tonight to talk about her expedition to prepare the astronauts. So welcome, Cassandra. We're just going to take a second while we switch screens. And I've got to remove the spotlight from me and put the spotlight on her. There we go. You are muted.
There, can you hear me now?
Yeah, absolutely.
Okay, I'm just adjusting two things, sharing my sound and putting on another window here for me. There we go. Let's do this. That's good. All right. Well, thank you so much for inviting me to speak at your RASC meeting, and I'm happy to be one of your newest members. I've been meaning to sign up for ages, and then it just, one of those things. So like Dave said, I am a geologist and a planetary scientist, so not an astronomer, but of course I love astronomy because they're related. And today I'm looking forward to sharing with you an experience. I just came back from this expedition to Northern Labrador. It was a geological research expedition, but also an astronaut training expedition. In early September, and it was led by Gordon Osinski, or Oz, those who are familiar with him, who's a professor at Western University, which before I came to the museum, I was at Western for over 10 years, and I basically not only studied there, but I worked there for many years. I ran analog missions, and I did a lot of field expeditions. And so this place, Mistaston Lake, which is an impact crater or an impact structure. It's actually my 6th time being there. And so I'm a bit of I did my master's degree on the rocks at Mistaston. And so you could call me I don't know, like the field guide of the expedition. And I had a bunch of different roles on this expedition, partly field guide, part camp manager, part assistant instructor. Oz really was the head of the astronaut training, and I basically chipped in wherever he needed. And then with my museum hat on, my role was outreach. So I basically documented with, camera, took photographic, video, and written, documented the entire trip, which is just under 2 weeks long. And so it's the material that I used to document that I'm going to share some of it with you today. A lot of it, I have hours of video to go through, and so I'll probably show you just mostly pictures, but explain a little bit what we did and why we did it. And part of the reason why I did it was just so that I could share on platforms such as these. So before I get too much into it, I just wanted to do a land acknowledgement. Ingenium, the Aviation and Space Museum, Canada Aviation and Space Museum, is on the traditional and unceded territory of the Algonquin and Anishinaabe people. And Mistaston Lake in Labrador, in the native Innu language, it's called Mistaston, is on the Mushrao Innu lands, and they call their homeland Nitassinan. And the expedition would really not have been possible without their support and their participation. So thank you to the Innu of Natrashish and Shashatchi. So Mistaston Lake is an impact crater. An impact crater is basically a hole in the ground created by a hypervelocity projectile. Mistaston itself is 28 kilometers in diameter, and the lake is 19 by 16. So the actual crater is somewhere out here. And we camped over here on the west coast. Mistaston is a very well-preserved impact crater on Earth. On Earth, we have all these geological processes, erosion by water, glaciers. There's been major glacial erosion here at Mistaston. But relative to that, it's quite well preserved. It actually has preserved ejecta deposits within its inner rim, which is not common at all on Earth. Very common on the moon, but not common very much at all. It's 36 million years old, so 36 million years ago, this impact occurred in northern Labrador. And so there's been, as I said, many glaciations since. It's arguably one of the best lunar analogs for lunar highlands on the planet. And that's because the rocks that were impacted consist dominantly of anorthosite. And anorthosite is the primary rock type in the lunar highlands. Not only that, is that on the moon, anorthosite is very common, but on the Earth, it's actually quite a rare rock. And Mistaston is only one of 2 known impact structures on the Earth to have this type of rock present. And the other one being Manicouagan, which is in Quebec. You've probably heard of that or seen satellite images of it. But there's, that is far more eroded crater, and there's far less anorthosite there, whereas Mistaston really is, it's a huge component that makes up a lot of the rocks that were melted and brecciated. And so that matters when you're trying to train people to look at rocks from the moon, because it's a better analog. Not only that, Mistaston is in a really remote location. So if you look at my Labrador map here, you can see this little box here, that's Mistaston here. Goose Bay, Happy Valley Goose Bay is down here. Nain, if you're familiar, is probably up here, and Natwashish is right here. Those are the closest communities. You definitely can't drive out there. You have to get there. You basically fly into Goose Bay commercial, and then you have to charter a Twin Otter or a helicopter to get to Mistaston. And these lands are the typical traditional hunting and fishing lands for the Innu, and that is really who uses this region the most. And because of its remote location, in addition to geology, you also get to experience isolation and some other remote training, including food. So when you're going on a long camping trip or canoe trip, you actually eat a lot of the foods that you might eat in space. And so it's good practice for space food, and I'll give you some examples. I'll try and give you the full experience from what it was like in camp all the way to what sort of rocks we looked at. So it was going to be a lunar crater talk, And so I've included some moon moon craters and moon talk into here, just to connect the two. But of course, because it's a lunar analog, it's perfect. But looking at the moon, and I believe this is an Apollo 11 image of the moon, I believe. If you look at the lunar surface, looking at planetary processes and surface processes, you can see that there's really only two dominant processes on the moon, and that is impact cratering, so bombardment by space rocks over billions of years, and volcanism. Both of those processes have slowed down quite a bit. You know, the moon, as far as we know, is no longer volcanically active, and impact cratering has petered down to about minimal levels. And so with those two processes, those are the processes that are going to matter when we go back to the moon. And as you know, the global space community, NASA and its partners, so Canadian Space Agency, of course, is included in that, are planning to return to the moon in person in just a couple of years with the Artemis program and Lunar Gateway. And so, although in the Apollo days, you know, geology was a big part of surface operations for astronauts, and they did a lot of geology training. And so for Artemis and its associated robotic missions, mostly aiming for the South Pole region of the moon, a terrain which of course is dominated by lunar highlands, Mistaston is the perfect place to go to study these things. And so these two processes, impact cratering and volcanism, that's what we need to train our astronauts for. So I'll only highlight two craters on the moon. These are two of my favorites. And both of these, well, particularly Tycho, I'm sure many of you have seen through your telescopes. Tycho is a really similar crater to Mistaston. You might notice that there's an uplift in the center, sort of a flat bottomed crater floor, and all these terraces in the inner rim. And so if I go back to the image of Mistaston for a second, you can see that there's an island in the middle. That's the central uplift of Mistaston. And this would have been sort of the outside of the crater. And so if I go back to Tycho, what you're seeing is the lake, if we were to compare these two, although Tycho is actually quite a bit larger, it's 85 kilometers in diameter, but structurally it's very similar. The lake would be, you know, this inner flat bottom part. And as we are exploring the region around Mistaston Lake, we're actually exploring this inner rim. So all of the images I'll show you is us walking on this inner rim. And so there's a lot of material that used to be in the center and then has been dumped out here. Tycho on the moon, of course, it's one of the younger craters. You know, maybe it's 100 million years old or so. And we know this because it's very fresh looking, and you've got those beautiful ejector rays coming out. Those are the things that stand out when you're looking in the night sky. Schrodinger crater, I put up there. It's not sort of a direct comparison to Mistaston because it has a peak ring central uplift, and it's much larger, 312 kilometers. It's actually on the far side of the moon, and it's an older crater, but it's within the South Pole Aitken Basin, which is the largest lunar basin, impact crater basin in the solar system, not just on the moon. And that's really one of our scientific targets as geologists, is this South Pole Aitken Basin. And Schrodinger is a crater within that, and it has within it evidence of fairly geologically recent volcanism. I'll point these out here too. This right here, these are rills. We think those are, you know, related to volcanism, and this right here may be a volcanic vent. And so it's one of those targets that has the best of both worlds, cratering and volcanism. So hopefully that might be one of the places that they choose to go to. They'll probably go closer to the pole, but we'll see. But whole package. So Mistaston, I had mentioned that I'd been there several times, but I've actually not just been as a field geologist. We've also done a series of lunar analog studies there in the past. It's just the first time that we've been real astronauts. So we've had analog astronauts at Mistaston. We're looking at the rocks, comparing them, doing comparative planetology between Mistaston and the moon in the past. But we were testing robotic and human scenarios, so such as robotic precursor missions. So you'd send a rover ahead of your astronauts to investigate, and then the astronauts follow up. Or you have a rover as an assistant, where the astronaut actually either teleoperates it from right next to it, or so on and so forth. Or you can send a rover afterwards. So those are the types of things. We were also testing decision-making processes and human health and performance monitoring. So we actually had some medical doctors join us as well. So just to give you an idea of the types of things that we actually have done at Mistaston, and it's been a very effective environment to do so. But Mistaston's not the only place where we train astronauts in Canada now and in the past. On the left side here, that's Charlie Duke and John Young from Apollo 16. That's them in Sudbury, in the Sudbury Impact Structure in Ontario. They're equipped with a lot of sort of analog equipment, to simulate them, having their suits and their cameras. And they're actually, they do have sort of a mission support in their ear. They were doing a variety of training there. And we actually had Canadian geologists helping them while they were there as well. And Apollo 17 trained in Sudbury as well. But of course, they had Jack Schmidt, who's the only actual geologist to have walked on the moon. And he definitely took a large part in training some of the other Apollo astronauts. And if he were here, I mean, he would tell you right off that the best way to go is just to send an actual geologist. But second best is to get these astronauts, whether they're pilots or engineers or whatever their background, astrobiologists, get them in the field and give them as much field training as a geologist as possible, because that's how you're going to increase the science return of these missions. This isn't the first time that we've trained our new Canadian astronauts either at a Canadian impact structure. So Oz, who I said is leading these training missions, he actually has taken Jeremy Hansen and David Saint-Jacques, two other impact craters. Jeremy, and I was lucky enough to be on several of those expeditions as well with Jeremy. He's taken to the Houghton and Tuninik impact structure in the Canadian Arctic, as well as Gow Lake in Saskatchewan. And David Saint-Jacques, he took to West Clearwater Lake impact structure in northern Quebec. All of these impact structures are great training grounds, but again, Mistaston really is the only one with rocks that are very much like the moon. But they all have their pros and cons. There's a lot less vegetation in the high Arctic than there is at Mistaston. So there's some trade-offs. So that's now 3 of our 4 active Canadian geologists that have been to Canadian impact structures for training. And Jenny is on the list to go in the near future, we hope. So I'm going to get to now this expedition while I've given the sort of intro spiel. And on our crew, this is all of them. It's a crew of geologists. So myself, this is Oz here. This is Niraja, she's from India. She's studying with Oz. This is Gavin, he's British. And he's just finished his PhD. This is Juan, he comes from Colombia. He was helping me practice my Spanish. And he's also a student with Oz. And these 2 gentlemen here this is Sebastian and Hank. They are Innu elders, and they came as guardians of the land with us on the expedition. They actually stayed in this sort of little cottage behind us. This is David. He's an archaeologist, and he made sure that we didn't trample any historical sites on our hikes, and hack at any rocks that might be important archaeologically. So he made sure we were on par with that, and he was also conducting his own research. And then all those people are sandwiched by 2 real astronauts. So this is Matthew Dominic. He's an American astronaut, one of the Artemis astronauts that was chosen. I think there's 18 of them. And this is our Canadian astronaut, Joshua Kutrik. And both of them are part of the Turtle group of astronauts. They were chosen in 2017, trained for 2 years, and graduated as astronauts in 2019. And both of these gentlemen may very well be the ones to walk on the moon. So let's go that. This is the Turtle crew, and you can see Jenny is also part of that crew. So Canadian astronauts, they train with NASA astronauts. They all live in Houston during their time as astronauts. So camp logistics. I showed you on the map we were camped sort of way on the west side of the lake. This is our base camp, and then the Innu. The reason they have a structure here, there's actually a couple of them, is because they hunt caribou during the spring and fall, and so this is where they come and stay. And I'm actually taking this picture from the airstrip. I'll call it I'll but I think I have a little video. We'll see if it works. So I said I was meant to document everything. So I not only documented by videoing everyone else, but I was trying to do little video blogs. So I'll give you a little bit of a teaser. We'll see if it works. And just give me a thumbs up, Dave, if you can hear it. Hopefully it plays. So it's the day before we spent the day today. We went on a small hike and then packed up all of our gear, a lot of the technical equipment, and we're just preparing for pull-out tomorrow. So we have a few Twin Otter flights gonna come in and pick up our stuff and pick up us, and hopefully bring us back to Goose Bay, where the following day I'll be able to fly back to Ottawa, back to Canada Aviation and Space Museum. It's a little windy and chilly here today. We had snow this morning, but it's warmed up a bit since then, so all the snow is melted. But you can see our camp in the background here. Those two big tents. One is our kitchen tent, and the other one is our tech and gathering tent. And all the smaller tents in the background, we call that tent village. That's where all the personal tents, that's where we sleep. And then there's a smaller tent up this way. You don't need to see it, but that's where everyone does their business. And then if I turn again, you can see there's Mistaston Lake, our beautiful impact crater in North Labrador. So see you soon, Ottawa. You can tell how windy it was. So Mistaston, or Mistaston in the Innu language, actually means where the winds never stop, just where the winds continue to blow. It's a very, very windy place. So. Sorry for that. I have an even cooler video. This actually happened just after I took that video. We were sending some of our equipment back. And so just to show you how we get in and out of this remote location. This is Josh standing on the airstrip, and hopefully this goes. There we go. And this is the Twin Otter. So yeah, that's the airstrip. It's basically a rubbly, relatively flat region, but it's full of shrubs and rocks and hunks of wood. And these planes have tundra tires on them that are amazing. They can just absorb just about anything. It's a really, really impressive aircraft. All right. The weather there. So in Northern Labrador, you never know. One day is sort of feels like midsummer, and a couple days later it's midwinter. We had hot days where I wanted to jump in the lake, although the lake is basically glacial temperatures. And then we had, mornings where I was hitting the ice and snow off of my tent. So we had quite the range. When it's not windy, there's a lot of black flies, so it's a very challenging environment, but it's one of the most beautiful places that I've ever been. The way that we get around for the most part was actually hiking on foot, and then we had a Zodiac. This is just a little, let's see if this works. Maybe not. Oh, okay. Oh, now it's working. It's just a time lapse of us trying to put this Zodiac boat together. And then the Zodiac turned out to not work very well because it was sort of the motor didn't really fit the boat. But we putted around enough to get to some exciting places. Anyways, the food. So as I said, in camp, there's no refrigerators. And so you're basically have to have shelf stable food, very similar to space food. And a lot of our food was freeze dried, dehydrated, or thermostabilized, which basically just means canned, where they heat it and seal it. And so this is, spaghetti bolognese made with texturized vegetable protein, which is dry. Tacos, same thing, TVP. Dried bananas and berries in our breakfast in the morning. This was a treat. These are real sausages, but these green beans here and these mashed potatoes, these were dehydrated foods that they would have stayed out there with us for months had we needed them, and you basically just add water and heat them, and that's very, very similar to what you get on space station. And then we got treated because I invited the Innu for taco night. They came back the next day. They had caught some Arctic char for us to share, and so we had that on the fire. But just to give you an idea of the sorts of things that we have out there. And now into the meat of the expedition. So although this was a geological expedition, that's not the only type of training that both the astronauts and all of the crew really got. Because we're in a remote environment, we have to live with each other in isolation. We're very far from help. If somebody needed to be evacuated out, it would be, several hours, possibly days if it's foggy, to get a helicopter in, sort of thing. So you're dependent on your teammates, and you're dependent on them for success, in this challenging environment with the cold and the bugs and various dangers, potential black bears and, just the usual scrapes and bruises types of things, dangers. Where in that environment, they need to do important science and exploration. And that's not that far off from what you have to do in space. You are put in a very stressful environment, and you're made to do work. You're made to do science or work, at a very high quality level. And so it's good training. They actually, as I was talking to the astronauts, they were telling me about a variety of the type of expedition training that they had been doing, caving and going underwater and things like that. And they said that, this was on par with that. But the trip, of course, we're also conducting some real scientific investigation. It wasn't just about training. We were doing real geology. Oz has a cratering research program, and with his students, they were doing thesis work. We were mapping and documenting a bunch of things. We brought back buckets full of samples back to the lab, and I'm sure those students will be in the lab for months to come analyzing them. So, but just to say, it's great to expose the astronauts to a variety of different scenarios possible. For the geology training, this was really immersive training, and the objective is to help them get the best science return from, a couple of hours to a couple of days on the lunar surface. They're not going to have a lot of time, so they need to get in, get the right stuff, and get out. And so the way that they start this, as part of that sort of, they're 4 years into their training now. And through that 4 years, they're actually in the early phases of their geology training. So they've had 2 one-week blocks of geology training. The first was more geology training that they would receive. So if you're on the International Space Station, they're basically doing remote geology, looking down at the Earth, things like recognizing, glacial geomorphology, different landforms on the surface of the Earth, or mountain building and things like that. So they started with block 1 was looking at that sort of thing. And then between them, that time and their next block, the actual announcement of the Artemis program came about. And so they actually tweaked their training so that the next block was focused on planetary science and planetary geology, with particular emphasis on impact cratering and volcanism, those 2 processes, the main processes on the moon that I mentioned. So, that makes a lot of sense, right? And so in that second block, they went to Meteor Crater, which is funny because it's your cartoon of the day, which I found really amusing. So that's one of the sites that they also went to for part of their training. And I've also been there many times myself. And where was I? Yeah, and so during that in class, they got a lot of theory on impact cratering. And so, the basics are, you have a hypervelocity projectile. When it impacts, you have a lot of high pressure, high temperature. You have which creates a shock wave. That shock wave and conditions, you're going to fracture, you're going to brecciate the rock, you're going to melt the rock, and you're going to vaporize the rock to a certain degree. And all of that material is then set in motion. A hole is excavated, essentially, and a lot of that material stays in the crater. A lot of that material is also ejected out of the crater or ejected into the inner rim. And in the larger events like Mistaston, you'll have an uplifted center. And so the resulting materials left are these broken up rocks, these rocks that we call melt rocks that were molten and then resolidified, but basically melted in the sense you can think of it as lava, but as a result of the impact. And these shocked rocks, so rocks that were subjected to very high temperatures in a very short amount of time. And that's the type of rocks that we focused all this training on and that they were looking at. It's basically how to be a field geologist. We took away all of the, the added stuff that you could do, the mission control in their ear and all of the other tools that they could have potentially used, like the fancy instruments, and just said, let's train you as a field geologist first, get you good with the rocks, and then they'll probably progress to that later because this is sort of earlier in their training. So every morning we started off with a morning discussion and plan. We looked at satellite images and topographic information from Mistaston, and depending on the weather and how cooperative the boat was being, we decide where to go and where to explore. And this is actually not that far off from how it would work with the moon. In the Apollo days, Lunar Reconnaissance Orbiter didn't exist, but now we have really high resolution images of the surface of the moon. So when we go back, I guarantee you, and it's already begun. They're looking at our orbital data of the moon, and they're planning out, where do we want to land? Where do we want to go? So they're doing very similar things. They plan ahead. It'd just be planned, not the morning of, but probably many months before. The first couple of days, we brought the astronauts and students to Cote Creek, which is a sort of a small river in the northern shore of the lake. And like this river and like all of the rivers that flow into Mistaston, there's a series of them. Each river has eroded down into the rock and has amazing exposures of these deposits that I was talking about.
So we have a question before you get too far through the slides. The geology training slide, I think that was with the one person standing there at the edge of the lake, right there. Yeah. Sure. What might be the layer structure above to the right of the human?
Okay, sure. I can explain this if you'd like. So what's going on here is you've got these mixed target rock. We call this a polymixed impact breccia at the base here, next to him. This is actually a contact. He's standing in front of a contact. This is Josh. Polymixed breccia, and then you have impact melt mixed into that breccia. And if you follow my line, it's roughly like this. And then it actually dips way down like this. This whole section above, that is impact melt rock. So you can think of it as that molten rock. So the breccia was ejected ballistically, and then so up and then down, and then had motion. So it continued to move and was deposited. And then not that long after, molten rock flowed over top. And this is the molten rock that flowed over top and the breccia beneath. And because those two flows were between them, it's quite turbulent. And so you get a mixing of both in between. And so that's what you get. You're getting a breccia and then a mixture of the two between and an impact melt on the top.
Okay, thank you.
No problem. Okay, and so that bottom breccia that I was talking about, that's actually what you can see in the background in this creek. So that image that I just explained, that's actually the same creek, but quite a further ways up. And so, but looking at this breccia hill behind this is Oz, Josh, and Matt. They're actually discussing we'd stop at every boulder in the beginning because they were asking, what's this, what's that, what's this? But these are just glacial erratics, just left by the glaciers, but they represent a lot of the rocks from the region. But this cliff face in the background is actually that polymic breccia, and you notice the color is very lunar-like. It's very white because the dominant component in it is a northosite, and when you shock a northosite, so when it is subjected to that shock metamorphism from the impact, it actually changes it into this whitish color. And if the really shocked northosites, they actually turn to almost like a powder. And so this creek is full of this stuff, and I actually have, I don't know if you'll be able to see it. It's actually behind me in my image, and then I'm holding a piece now here. It's not, this one's not that shocked, so it's not as white, but it's a very light colored rock. Very similar to the rocks on the moon. And so I thought it would be fun to do a brief example. So the top three rocks, those are actual Apollo samples. Top left this is shocked anorthosite, a breccia. So breccia is just a lithified mixture of broken up rocks, and it is held together by smaller broken up rocks, essentially. And sometimes you can have fragments of that melted rock in it, but we give it a different name. But you can see that the different fragments are in here. And this is actually a lunar mare basalt, or at least that's how they've interpreted it. You can see that there's giant voids in those. Those are trapped gases when it was solidified, and we call that vesicular basalt. And below are three examples of rocks from Mistaston. So this is shocked anorthosite from Mistaston. You can see they're very similar. This is a breccia. This is not as close up, but actually if you did cut that, it would have the same texture. And then this is one of the vesicular melt rocks at Mistaston. And though it is not a volcanic rock, melt rocks are very similar to igneous rocks. And if you didn't know you were standing in a crater, most people would think that they came from a volcano. And so I'll show you another one. This is from Mistaston as well, that looks very similar. It just has, the vesicles are just a little bit bigger. If you're looking at my screen now, because I'm holding a rock up. That's the last one. It's trying hard to, I wish we could do this in person, so I would hand rocks out next time. Okay. Another place we brought everyone was Discovery Hill. It's this giant butte, that just rises out of the lake. It's quite the sight to see, and it has 80 meters thick of that melted rock, that molten rock. And you can just imagine that there's this big body of lava that flowed out of the cavity and was deposited up on the rim here. And at one time, this, that molten rock, that would have been all around the crater and in it. And now, after glaciation, for some reason, this particular butte was spared, and so we get to explore it ourselves. But you can see that everyone's sort of crowded around a rock, and we had constant discussions. It was also a really interesting place to hike, because the exposure is cliff face all the way around. So you're either at the top of the cliff or at the bottom of the cliff. Very interesting that way. And like I said, pretty much every single day, everywhere we went, there was constant discussion. And it's not us so much telling Josh and Matt and the students, this is what this is. It's us saying, hey, what do you think this is? What do you see? What textures do you see? Can you describe it? Use as many words in your own words. One of the things with training field geologists is you don't actually need to have the proper terminology. You don't need all the jargon. You just need very descriptive terms. So if anybody can understand what you're describing, then the geologist will figure out and they'll give it the better name later, right? You just need to be descriptive. And if you're a detail-oriented person, you're probably, and an observant person, you'd probably be a great geologist. And that's basically what we did everywhere we went. We'd ask them, what do you see? What do you think that means? In addition to having these discussions and of course just familiarizing themselves with the rocks, they did get more concrete skills. And so learning to, when you approach an outcrop, we actually do have sort of a system of rules that you need to follow when you're documenting and sampling something. And so they learned to take field notes and document everything. And Western actually had developed in the last couple of years this iPad app for field geologists. And it works really well because it also helps you have step-by-step the order of things you're supposed to do. So when you get up to an outcrop, you first take, a big picture, you take a GPS coordinate, which the iPad does automatically, but you just click it in. And then it'll ask you at every step to add description, be descriptive of every stage. And then you get closer and closer to the rock. You described on a much smaller scale. You add the scale to the photo. It took the photos, it documented, it did everything. And so they, with repetition, they got this down really fast. And of course, they learned to put scales in their photos, and they would ask different people to jump in their photos that were, a pen, anything, so that the size of what you're looking at. That's one of the geology rules. Next to that is what samples are important to collect and why. So how to properly document, collect, and store samples. And this is one of the biggest things for the moon, because that's the main thing they're bringing back, right, to a scientist back at home. And that's what we're going to get really excited about, is when they bring the rocks back. And so we want them to pick the right ones. And we do this beach test. We go on the beach, which is full of pebbles from not just Mistaston, but the wider Labrador region. We say, okay, let's say you're on the moon, you see all of these rocks here. Which ones do you take? How do you decide? And the key is you take representative of each type that you see. There's no limit on, they will be limited on how many rocks they can take, but it's important that they get one of everything. And so we'd practice by them going through pebbles. And even though that's not, the actual rocks that the geologist would take, it was a really good exercise. Some of the places were really hard to get to, and some of the days were very physically challenging. Like I said, this is still Discovery Hill, but you'd have to hike all the way up the hill and then hike off the cliff face and then around, where every step you took had to be very stable, and you had to be very, very careful. And another day, we actually were exploring into the unknown. The boat wouldn't work, so we decided to hike up into the rim of the crater and explore some outcrops that I hadn't actually been to. I've covered a lot of ground, but this is a very big crater. And so we were exploring all together. None of us had been where we were going, and we were looking for new outcrops. And so we actually did sort of this bushwhacking hike, which bushwhacking, not so much of an issue on the moon, but physically challenging exploring is. And so, it does have an analog equal, let's say, anyways. But we did like a 20-kilometer hike that day, and still all smiles, pouring rain, 0 degrees outside. We had to do river crossings. Anyways, there was a lot of physical challenges, but they rose to every challenge, and they learned very, very quickly. They adapted. They're very intelligent people, of course. Most astronauts are. And it was just an absolute pleasure to be able to assist in some small part of their training, and keep them fed, that sort of thing, during the mission. I didn't on purpose go too deep into the actual geology at Mistaston, because I didn't want to get too rock heavy, but I'd be happy to answer any more rock questions that you have at the end. But again, so here's our core geologists and trainees, and this was an amazing team all around. Actually, this is one of the best trips I've ever had up to Mistaston, and I hope to do it again. And I do know that Oz is in talks with the Canadian Space Agency and NASA to make this a sort of a regular thing. So, and although I am of a mind that, when we go back to the moon, it's always going to be the better thing is to send the actual geologists, and that would generate the best scientific return. But with the right training and a lot of field exposure to these sorts of experiences and field geology, I'm confident that they will bring back some really good samples and we'll have a really good science return. Yep. That's the end of my general talk. I'm going to put a shameless plug in here because I know that you have so many wonderful astrophotographies within your group, that the museum is running a tweet share right now. So if you wanted to share one of your amazing photos, like Pierre Martin, this is an older Perseid meteor shower image of his. We'll be running this month-long thing. And I know that Sky News also has the astrophotography special edition out last month and this month too. And Jenna's been tweeting these amazing astrophotography videos. So I love it. Everyone is all astrophotography right now. So anyways, if you are interested to share, please do, whether it's a tip or an amazing photo like this one. And I'll share you. I am an amateur, less than an amateur in astrophotography, but this is an image I took from Mistaston of the Northern Lights, and I almost caught the whole Big Dipper, but one of the stars is hiding behind a cloud. I think my tripod moved a smidge because the tents are a little blurry, but I'm a beginner. So starting Aurora, and then I got one more with a satellite in the background. That one's actually much more crisp, so that one worked out. Anywho, if you want to share yours, this week it's Milky Way themed, and there'll be other themes every week. So thank you so much for inviting me and hearing me out, letting me share my experience. And I just wanted to say thanks to my partners. This expedition would not have been possible without Western University, the Canadian Space Agency, the Polar Continental Shelf Program, of course, Ingenium, and the Innu Nation, and my amazing field crew.
Well, thank you very much, Cass. Wonderful talk. And I'll just go to pause for a second here and see if there's any other questions for you. I don't see any. Oh, how do we participate in the tweet share?
Oh, so if you go to Aviation and Space Museum's Twitter account, which is AV Space Museum, at AV Space Museum, there was a tweet that went out on the 29th, and we'll just keep adding to that thread. You just reply to that tweet with your own tweet.
Okay. Thank you very much. Okay, so there we go. Chris is going to bring up his slides then. So thank you, Cass. You're welcome to hang around. We've got some amazing astrophotography coming up. Maybe you'll suggest that some of those folks could submit. Okay, folks, we are just a second here. There we go. We're moving into a 5-minute break. So as we usually do, there's a Messier and Moon challenge. So if we go to the next slide here, you got 5 minutes to figure out what these two images are. Which Messier object is it, and which moon crater are we talking about? So 5 minutes, and we will return. See you then. Okay, Chris, if you can move on to the next slide. There we go. So there's the answer to our M&M challenge. So we're just going to pause here for just a second. I just need to let my panelists know which order they're doing their presentations. So I'm just going to send them a quick chat message here. And then we'll get things underway. Oh, there's the order right there, folks. So that's okay. So we're going to turn over to our observation reports. I'm going to start with Jim Sophia. So Jim, let me just highlight you just a second here.
Okay, you hear me well?
Yes, no problems there. So let me just spotlight you. There you go. Okay.
Okay, fantastic. So this is one of my favorite summertime objects, summertime favorites. It's the Lagoon Nebula, known as M8, which is an emission nebula in Sagittarius. And this is a 2-minute exposure taken in mid-August with the Malincam Skyraider camera on a 6-inch Smith-Cassegrain scope using the IDEAS NBX filter. M8 is a large emission nebula composed primarily of energized hydrogen from the radiation of a nearby young and massive star known as Herschel 36. M8 is about 5,000 light years away and spans roughly 130 light years in length. In this image, you can also see several block globules, which are small, dark nebula having various irregular shapes, as you can see. And these contain dense cosmic dust and gas from which star formation may take place. Next one, please. This is the Trivet Nebula, known as Messier 20. And this is also a 2-minute exposure using the same equipment and filter as in the previous image. M20 contains an open cluster of stars, an emission nebula, a reflection nebula, and a dark nebula. The dark nebula, known as Barnard 85, is seen in the apparent gaps which form the petal-like appearance of the Trivet. Next one, please. And this is the Elephant Trunk Nebula, IC 1396. And this is a 4.5-minute exposure using an 8-inch Smith-Cassegrain telescope and also using the Malincam Skyraider camera with the Optolong L Extreme filter. Amidst the concentration of interstellar gas and dust lies a dark, dense globule that somewhat resembles the trunk of an elephant, which is seen in the center of this image. The Elephant Trunk Nebula is located in the constellation Cepheus and is approximately 24 light years from Earth. Thank you.
Next is Richard. Just a second here. Let me just spotlight you. There we go.
Great. Okay. So I've just had a lovely summer. Towards the end of the summer, I spent 3 weeks at a cottage, which is only a couple of kilometers away from the North Frontenac Dark Sky Preserve. And it shares the same lovely dark skies. I also went up to the Dark Sky Preserve platform several nights and also saw them using the, our old 16-inch telescope is now installed in a lovely roll-off roof observatory there. And they were getting quite a number of people coming to have a look through it. So I was very, very glad to see that in use. Anyway, I took most of my pictures using my equipment, the William Optics Z73 telescope with my Canon M100 camera. And this is an object that I haven't really seen too many pictures of. It's the Helix Nebula. And right now it's in the south. It's very easy to find because it's just about halfway between Jupiter and Fomalhaut, and just a tiny bit east of the line connecting those two. It's a planetary nebula, but unlike a lot of other planetary nebulas, this one is big. This is a full frame view from this small telescope, and it really comes out very, very nicely. I'm not quite sure about the colors. I'm having a bit of trouble with color adjustments and the post-processing, but it's a distinctly greeny blue color in the eyepiece as well. Next one, please. Now, this is my summer project. I've been trying to get some good pictures of the Veil Nebula in Cygnus. And it's actually just a bit too big to fit into one field of view. So this is a panorama of several shots pieced together, which has been a very, very difficult challenge for me in learning how to use all of the image processing techniques. But I do have now the three parts of the Veil Nebula: the east arc, the west arc, and something in the middle called Pickering's Triangle. There are a bit more wisps of nebulosity towards the south, but I didn't capture those. So, but I'm pretty pleased with how this turned out. This is a supernova remnant from many, many thousands of years ago. Next one, please. And then there's also Jupiter and Saturn well placed in the south. So I've been learning how to do the lucky imaging, taking short videos, and then stacking up just the few best frames off the video. This one also uses a longer exposure and combines it with the image of the planet to show the moons around it. And I was very happy. For the first time in my life, I've actually caught an image with a shadow of a moon. So there's Callisto's shadow, a little black dot in the south, and the moon Callisto is off to the right side. Then, of course, the other three are visible too. Next one, please. And doing the same with Saturn. I am not getting quite as good results with Saturn. It's a bit smaller, a bit dimmer. It's harder to get a very short exposure and still see very much. But with a longer exposure, I was very happy to see that I could spot many moons of Saturn. This particular image shows 4 of them, but on another occasion, I've actually managed to catch 6 moons. So we'll see if I can still keep improving on that one. Next one. Now, the lunar challenge for this month were the craters Klaproth and Cassatus. I hope I'm pronouncing that correctly. There are 2 craters right on the very southern limb of the moon, farther south than Clavius. Of course, the brighter crater at the top is Tycho. But when I took a picture in September to try and catch these, they're really off the edge. They're way far south, and you really can't make out the shape of the craters at all. I thought, oh, that's not really fair to have us try and shoot craters that aren't visible. But then I was reminded of the talks we had earlier this year about the southern mountains of the moon and how the libration of the moon keeps shifting them in and out at different seasons. Oh, well, if I look back in my files 6 months ago, I should be able to see them. And sure enough, for a picture in April, they are quite easily visible because the moon is tilted, so the southern hemisphere is showing more in April than it is in September. So there they are. I made the challenge. Okay, thank you very much.
Okay, thank you. So I'll go turn it over to Jim just a second here. There we go. Jim Thompson.
Good evening, everybody. I have just a couple images to share tonight. This first one is a composite of the sun as it appeared on Sunday, August 15th. Conditions were partly cloudy with good transparency, but poor to below average seeing. The purplish colored version on the left was captured using a Bader Planetarium Herschel wedge and an Omega optical calcium K pass filter on a 98 millimeter refractor with an ASI 290 monochrome camera. This is a stack of the best 10% out of 3,000 frames. The magnetic activity surrounding the very small sunspots that were present that day is visible in the image in the form of the bright plages that you can see sort of in the upper midsection of the disk. I like imaging in calcium K because the granulation is very easy to see. Plus, you can make out mega granules. So if you look at the plages, they sort of outline larger sections of the sun's surface, inside of which is the smaller granulations, and the mega granule demarks a much larger region of convective activity in the photosphere. Also interesting to note is that there were prominences visible on this day in calcium K. You can see the brightest one is the faint grayish blob in the upper left. Now this is, it's rather unusual to see prominences in calcium K. It requires the prominence to be very bright to be able to see it. So when I started out the day in calcium K, and I thought, oh boy, I wonder what I'm going to see in hydrogen alpha. Just a note, to capture the prominences in both of these images, along with the disk, the face of the sun, I use two different exposure times. So the prominences are taken at about 10 times the length of exposure that the face of the sun was. And they were composited after the fact. Moving to the gold colored image on the right, this was captured using the same telescope, but moving to a 50 millimeter aperture hydrogen alpha etalon with a blocking filter. By comparing the two images to each other, you can see how the appearance of each phenomenon changes depending on the wavelength of light being used to observe. For example, in the location of the bright plages that we see in the calcium K image, there are long, twisty fibrils in the hydrogen alpha image. What I found really exciting in the hydrogen alpha image was the massive and intricately detailed prominence off the western limb. Despite the poor seeing conditions, I popped in a 2.5 times Barlow to examine this area in more detail, and we'll see that in the next image. But before we leave this image, I would like to point out the difference in the sharpness of these two images. They were both captured using the same technique, the same telescope, and the same camera. The reason for the difference in sharpness is that the poor seeing has more of an impact on short wavelengths, i.e. calcium K, which is down around 397, I think, nanometers, than longer wavelengths like hydrogen alpha. So the hydrogen alpha image is sharper because it's less impacted by seeing. Okay, next image, please, Chris. So here we can see it, the close-up now of that prominence. I've rotated it so that it better fills the screen. I've added the Earth to scale to the image so you can better appreciate how big the prominence is. So when I said that the prominence was massive, I meant it was massive. Again, this is a composite, so the solar disk and the prominences were captured at two different exposures and then composited later. Next image, please, Chris. So this is my final image. It's a composite of a number of captures I made of Jupiter and Saturn. It was on the same date, August 15th, just later in the evening. Now, these were captured using a 10-inch Ritchie-Chrétien scope and an ASI 462 color camera. The views on the right side of the image were captured at the native f8 of my scope, and the views on the left were captured after adding a 2 times Barlow. All of these images were produced by stacking the best 10% of 3,000 frames, stacked and auto-stackered and sharpened using wavelets in Registax 6. And that's it. Thank you very much.
Okay, thank you very much. We're going to move on to Andrea.
Hello, can you hear me okay?
Yep.
Oh, good. So this is a nebula also in Cepheus. It is called the Lion Nebula and also known as Sharpless 2132. And it's a very faint emission nebula in Cepheus. It's actually really close to the Elephant Trunk Nebula that Jim was shooting. This was shot with my mono, and I shot about 3 hours in hydrogen alpha and 3 hours in oxygen, and then I mapped hydrogen to red, and that gives you the red nebula, and oxygen was the blue. And this was really, really quite faint, and I think I need several more hours, but I ended up last night, I was able to take some sulfur data, so eventually I'd like to incorporate sulfur data to do a tricolor image, but I am not quite there yet. So next image. And this is the Heart Nebula in Cassiopeia. I always think of the Heart Nebula in Perseus because if you know where the Perseus double cluster is, it's just sort of right beside it. This is a very, very large emission nebula just below the W of Cassiopeia. This was shot with the Red Cat telescope, so about 250 millimeters focal length. The ASI 2600 MC Pro camera, which is an APS-C sensor, and I use the L-enhanced filter, which is a filter that allows hydrogen and oxygen to go through. And this is a very big nebula, but often you'll see close-up the Fish Head Nebula, which is in the lower right-hand corner. And the very of this nebula is a star cluster known as Melotte 15. And you often see a lot of very deep images of that area because it's quite spectacular as well. Next image. The next couple of shots, and I think Chris put in a fourth shot, are Milky Way images that I took this summer. Some of you know that there is a Milky Way season. In Canada, it's generally from about March to October when you can easily see the core of the Milky Way. This image and the next one both have similar characteristics in that you just don't go down to the beach and take one shot like this. You have to typically do a blend. You would take one image that is exposed for the foreground, so you'll need a lot of light to light up a beach at night. And then you will have to do a different exposure for the sky. In this case, I used a bit longer focal length than people normally do. You often see people use a 14 millimeter camera lens or a 10 millimeter camera lens. And this was shot with a 35 millimeter camera lens, which means you get a much bigger and more dramatic Milky Way in your photo. But the downside of 35 millimeters is your single exposure can't be longer than 9 seconds, or you'll get star trailing. So what you have to do is you have to take a series of 9-second images and use a stacking program. And that's what I did to get this image of the sky. There was something else. I just wanted to say that this is a camera. This camera was my normal, regular DSLR camera. It's something I've had for years. And if you own a camera like this, you can try taking these kind of photographs as well. Next image. And this a similar picture. It was a real close-up of the corn, and I would have to obviously expose the corn. I would do a long exposure, and this was lit by starlight. There was no moon, so by leaving the lens open for a long period of time, you can get all the light you need to light up the foreground. However, the sky would be blurry, so you would then have to do a separate exposure again for your sky. And the Milky Way season is almost over, but you probably have maybe one more weekend to try and get out and do this with your own camera if you'd like. That's it for me.
Thank you, Andrea. I'm just going to turn it over to Bob Olson. Give me a second here. There you go, Bob.
Yeah, how do you do? This is my picture of M15 that was presented last month, but I wasn't really looking for that. Next slide, please. Yeah, what I really wanted to take a picture was of Peas 1. It was the challenge object by Oscar. I found M15, no problem, but I didn't have enough time last month to actually tease Peas 1 out of it. Next image. So really, to do that, you've got to zoom in a bit to get more of the M15. Next slide. And so this is the close-up of the crop M15's core. Next slide. We can find Peas 1 by overlaying an image from a reliable source, so that you know where Peas 1 is. Next slide. And so when you take away the image, you see your line leading to basically a big blur. There's too much light in there. And this is as far as I got last month before David started calling for images. So next slide. So this month I started off with an unstretched image of the same area. And now it starts to show up a little bit. Peas 1 is that faint blue area at the end of the line. It's pretty small and pretty faint. Next slide. One of the characteristics of a planetary nebula is that they have a lot of O3 light. So an O3 filter can be used to blink the image, and the planetary nebula will dim less than the stars around it. So Chris, could you blink this back and forth a bit, please? Okay, again, just a couple of times. Now you will see that the planetary nebula is also dimming, but it's dimming less. That's good right there, please. But it's dimming less than the stars. And so this is definitely Peas 1. Now, next slide, please. So I told Attila Danko that I had tracked down Peas 1, and he informed me that in 2008, I had found Peas 1 for him by using star hopping throughout this mess of stars. And I look back in my records, and he was right. I had found it back then. I don't remember what I had for lunch 3 days ago. How does he remember what I imaged 13 years ago? It's really hard to believe. Okay, next image. This is the Crescent Nebula. It's about 5,000 light years away. It's the shock wave from a Wolf-Rayet star in the middle there. It's found in Cygnus, the Swan. It's nice position to image right now. Thank you very much.
Okay, thank you. And I'm going to turn it over to Taras.
Hi, can you hear me?
Yep, no problems.
I took this picture of Uranus September 16th with the FLO's 18 Star Master telescope. I intentionally overexposed it so that the moons of Uranus could be seen, and they showed up in this picture along with some stars in the background. Next slide, please. I was able to identify them using Stellarium software. These are 5 of the brightest and largest moons of the planet, with Miranda barely showing as a dim dot through the planet's glare, being the smallest and the dimmest among the 5. This moon is only 472 kilometers diameter and was of 16.5 magnitude. The distance from Earth to Uranus that night was 2.8 billion kilometers, or almost 19 astronomical units. So it's amazing how the light of such a small and dim object has reached us after traveling such a distance. Let's go to the next slide. I also imaged Uranus with normal exposure, hoping to reveal some clues on what its surface may look like. The visual image after stacking did show some subtle differences in red channel, although after stacking and merging all the three RGB channels, there was practically no visible details. So I imaged the planet with an infrared filter, 850 millimeter wavelength, and it did show up some darker and brighter areas, which I later mixed to the red channel to highlight the difference. This resulted in this image that you see. While stacking it, I used the drizzling technique. This is when the resolution of final image can be increased if the quality of source data was high enough. And in this case, it resulted in somewhat larger picture than the original individual frames. Let's go to the next slide. So except for infrared, I also imaged the planet with a yellow filter, because yellow is the opposite color of the blue and it can show a little bit more of the contrast. So that night, I hoped for better contrast. The yellow is the image on the bottom left. It's actually through, it's in the yellow because of the yellow filter. And you see a little bit, I added that data to mix it with red and green channel, as yellow can be made out of those. And it showed up in this barely visible atmospheric hood on the planet. It can be seen more prominently. On the top left, you can see the stacked infrared data, and it does clearly show the difference in infrared. Difference in brightness between the two hemispheres of the planet. You can see a subtle gradation in red channel also that I mentioned earlier. Let's go to the next slide. 3 nights later, on September 19th, we were in for a treat. The seeing conditions were unusually favorable as for our location, and I would say 8.5 out of 10. And they were the best I've seen near Ottawa so far. So the planetary pictures turned out quite well as well. And observing them visually, observing the planets visually was, an unforgettable experience. Paul will tell you more of the story in the details, and as he was also that night at FLO as well, using his newly set 14-inch mid telescope. And we kept sharing our excitement about how lucky we are to witness such a rare show when the planets would reveal their best features very clearly, like Saturn did its Cassini division in this picture. I also highlighted the moons in the configuration as they were seen that night. Let's go to the next slide. Jupiter not only looked great, but had a lot of things to show that night. Its great red spot, the details in the bands, transit of its moons. You can see Europa beginning its transit in this picture. It's that bright dot closer to the planet's edge on the left. Shortly before that, we saw how it started its transit by kissing the edge of the planet. The moon was the moon on the left, far left, is Ganymede, and there was also Eos somewhere in planet's shadow around that time as well. Let's go to the next slide. When Jovian moons leave planet's shadow, it's quite an unusual event to observe as well. The little dot suddenly appears out of nowhere close to the planet's surface and brightens up within a span of less than a minute. Even though such events happen relatively often, observing them is quite a treat, and that night we were able to witness that as well. Can you please play the video, Chris? So this 20-second video is 4 times speed of my original recording of such event. The planet itself looks overexposed, but I did it on purpose so that the moons would appear brighter, and you'd be able to see Io exiting from the shadow more clearly. In reality, this took about a minute from the moon's being completely hidden in the shadow to its full brightness. The orbital period of Io is known to be 1.769 Earth days, so almost 2 days. So one could assume such events can be observed with exactly such frequency. Let's go to the next slide then. However, Danish astronomer Ole Rømer, while measuring timing between such events as the eclipses of Jovian moons, noticed that there is a strange discrepancy with that number. When the Earth was nearest to Jupiter, such eclipses of Io would occur about 11 minutes earlier than predicted, and 6.5 months later, when the Earth was farthest from Jupiter, the eclipses would occur about 11 minutes later than predicted. Rømer knew that the true orbital period of Io could have nothing to do with the relative position of the Earth and Jupiter. In a brilliant insight, he realized that the time difference must be due to the finite speed of light. That is, light from Jupiter's system has to travel farther to reach Earth when the two planets are on the opposite side of the Sun than when they are closer together. Rømer estimated that light required 22 minutes to cross the diameter of Earth's orbit. The speed of light could then be found by dividing the diameter of Earth's orbit by the time difference, and Rømer came up with a number of 4,800 to 103 leagues per second, or about 222,000 kilometers per second. Rømer's determination of the speed of light was the demonstration that light has a finite speed and so does not travel instantaneously. Let's go to the next slide. And yet, that was not all that wonderful night. As we were getting all ready to leave, I've already packed up my camera. Paul did take the last peek at the planet through his telescope and shouted, "Trust, is that Jupiter's moon shadow close to its limb?" And indeed it was. It could clearly be seen visually as a dark spot on the very edge of its surface, and I felt obliged to image it as well. For the time I was ready to image it, it moved a bit farther, and it was from the very same Europa moon that we saw transiting the planet earlier. The moon itself moved now that far that it could drop the shadow on Jovian's surface from its location on the orbit. And it was an event not to miss, and a great highlight of that wonderful night. Thank you.
Okay, thank you, Taras. So I'm going to turn it over to Paul Cloninger, and I'm going to show a static image. It's got my name on it, but it is him. And there we go.
Great, thanks, Dave. Well, good evening, everyone. We've had some pretty decent nights in the last month for observing and imaging, a sample of which you've seen in the very fine images submitted this month. So I thought I'd take this opportunity to share a few also, as well as provide you with an update of the latest developments at FLO regarding our latest equipment addition out there, the 14-inch LX200 GPS Paul Commission Memorial Telescope. Paul bequeathed us this lovely high-end instrument to the club, and after a lot of work by numerous members to build a deck and the Skyshed Pod Observatory to house the instrument, I'm very glad to announce that it is now very close to operational status. After the construction of the deck platform and the erection of the Skyshed Pod, Chris Tarrant and I have been working on getting the scope operational since early summer. This included setting it up on its mount, testing its electronics and motors, polar alignment, and so forth. We certainly ran into our share of snags along the way, including the discovery that the scope's firmware was suffering from a global issue that reared its head in 2019. Some of you who own go-to scopes are probably all too aware of this bug, the dreaded GPS weak rollover issue. Long story short, this is a weakness in the way time is counted in the GPS network of satellites. And it means that about every 19 years, the year indicated on devices using the system would not show the correct year. In fact, rolling the clock back 19 years. This was a known issue with the system and one that could be easily corrected with a firmware update. Unfortunately, the 14-inch scope's computer had not been updated to correct this issue as the scope was not active in late 2019 when the rollover occurred. So as it turned out, Chris and I had to take the scope back down from its mount, and we hauled it out to his place where we could get an internet connection to properly run the firmware update. With that in the bag, we then had to haul the beast back to FLO to reinstall it and perform the necessary alignments and testing. Not an easy task given the scope's weight. The optical tube and mount are not meant to come apart, so you have to move them out as a single unit. But it finally came together, and Chris and I have since been out there doing more refinements and testing of the instrument. A number of members already got a bit of a sneak peek at the facility at the 50th anniversary FLO celebration last month, where we even got a few brief first light glimpses of the moon and Venus through the scope. So I just want to share with you some test images I've taken to give you an idea of what the scope can do. And as you've already seen, Taras has also shared some views taken through the 18-inch Star Master out at FLO. Together, these two scopes can provide stunning views for the members, both visually and with the use of imaging. So to this end, the following two images were my first attempt at imaging through the 14-inch scope since we've set it up. These were taken with a Canon 70D8 DSLR 2 weeks ago on September the 16th, after Chris and I finished some mechanical work on the instrument. They're just really quick and dirty single image shots, so no stacking here. And they allowed me to test the pointing, aiming, and focusing of the instrument. The seeing was reasonably good that night, and the moon provided an easy and rewarding target for this work. A lot of nice detail was visible in the polar regions and along the terminator. Next slide, please, Chris. The battered southern highlands were also rewarding and made for a nice view of Tycho crater and its rays, and the numerous craterlets inside magnificent Clavius further down to the south. I was also seeing the system capture some very fine, detailed relief visible near the South Pole at the bottom, the area that Cass was talking about as potential targets for the Artemis landings, and an area that Jim and Thompson and I focused on earlier this year when we presented our three-dimensional views of the South Polar region. Again, these images tonight are just single images, and I really look forward to capturing the moon again at high resolution to see even finer detail by capturing sets of subframes for stacking. Even just visually, though, the view through the eyepiece on this night was very bright and stable, and it felt very three-dimensional. Next one, please, Chris. So this image of Jupiter was also a single image taken with the Canon 70D. This is not my preferred camera for planetary imaging, but Jupiter was there and it was calling, so I couldn't really ignore it. The camera still managed to capture some good detail in the bands of Jupiter and the Great Red Spot, along with the 4 Galilean moons. However, 3 days later, on September the 19th, the sky was a game changer, as Taras has already mentioned. The clear sky chart predicted above average seeing at FLO, a rarity in our part of the world, and so I headed back out to FLO to check it out. Taras had also tuned into this promising forecast and was already at work on the 18-inch Star Master when I got to the site. We were not disappointed. Next one, please, Chris. So the seeing on that night, to say it was superb would be an understatement. It was just incredible. The eyepiece views through both scopes were stunning. The air was very stable and made for some great views through the eyepiece. Fine details were visible on the entire planetary disk. Fortunately, I brought one of my favorite planetary cameras, the NexImage 5, that night, and managed to capture a number of video sequences that would allow stacking and processing of many combined frames. Next one, please, Chris. Along with the Great Red Spot and the belts and zones right up to the polar regions, 3 of the Galilean moons also shared the view, including Europa, transiting across the planetary disk. This was one of the finest nights that I've ever observed Jupiter, and with the high magnification available through the 14-inch, I was able to observe fine structural detail in the belts and the zones, details that I had never managed to see before. It was really a rare night. After I shut down and removed my imaging camera from the scope, as Taras mentioned, I decided to take one more visual peek at Jupiter and was greeted with a view of Jupiter's shadow just starting to appear on the western limb of the disk. I shouted this out to Taras, who was still imaging, fortunately, and as you've seen, he managed to capture a fine view of the shadow creating an eclipse on Jupiter's cloud tops. Really nice capture there, Taras. Next one, please. So one final target also beckoned that night. Though its atmospheric features aren't nearly as pronounced as Jupiter's, it makes up for it with its rings. But even the subtle atmospheric details were visible visually on that night, and the rings were just mesmerizing. The shadow cast by the rings was easily visible on the planet's disk, and the disk's own shadow was easily seen on the far side of the ring plane. Just a superb view of the Lord of the Rings that night. So where are we with the 14-inch? Well, Chris and I still have some technical details to work out, including conducting some precision polar alignment testing and implementing the scope's smart mount capability, which enables very high precision pointing. I then want to test the system for long duration imaging, including auto guiding, which will be available on the unit. We're also currently preparing a quick start manual for those who will want to use the scope. And to that end, we also plan to hold training sessions to give you hands-on familiarity with the scope's operation. So I hope that these images that I've shown tonight and those shown by Taras give you a sense of the capabilities of the two instruments that we have available at FLO now. Our facility has come a long way with the recent upgrades performed there, and soon yet another fine instrument will boost capabilities even further. Work is currently underway to install the fine 6-inch refractor bequeathed to us by Rolf Meyer. Exciting days are ahead for us at FLO for sure. So I have one last note, not another image, but one last note, somewhat related to the 14-inch. So Oscar posed Einstein's cross as last month's challenge object. Oscar, if you're on board tonight, man, I gotta say, you would be hard pressed to see or image this extreme object. It's tiny and it's elusive, and it's buried in the core of a very distant galaxy. I've actually tried to image this with my 11-inch on several occasions. I think I've come close, but its tiny size is likely just beyond the 11 inches resolution limit. But I haven't given up. The 14-inch at FLO might just do the trick. We'll see. Thanks, everybody. Clear skies. Stay safe.
Okay, well, thank you very much, Paul. Okay, sorry, it took a second for my image to come back in here. So these are last month's observing challenges. Unfortunately, this month we do not have any challenges. So you've got a month off. We had a little bit of mix up with Oscar on the dates and so on. So hopefully next month, Oscar will come up with some more challenges for us. These are the ones from last month. The RASC calendars, the deadline to order them is October the 15th. And for members, it's $16 for one, $30 for two. For non-members, it's $20. There is no discount price for non-members. There's 4 locations in Ottawa that you can pick the calendars up from. Deadline is October the 15th. So you've got basically 2 weeks from today to order the calendars, at which point we'll place the order, and the people whose places you're picking them up from will alert you to the fact when they come in and arrange for pickup. The Fred Lawson Observatory flow is available to members. Limit of 100 people on the site outdoors and 5 people with masks on in the observatory. And yeah, we encourage you to get out there and check out some of the new equipment and layout of the site. So flow started, these are member only star parties. The next one is planned for October the 9th. We have a waxing crescent moon on that evening. These are some of the folks that keep the club running. I'm hoping we'll see Ann and Art Fraser at some point in the next few months when we get back at the Canadian Aviation and Space Museum. Right now, we do not have a date for in-person meetings, but I'm looking forward to the time when we'll be able to do that, meet face to face. The audience, Chris, I think
the maximum number I saw tonight at any one time was 79 people.
79, yeah. And plus we have people on YouTube as well. So And thank you to everybody who participated tonight. Special thanks to Dr. Cassandra Marion, our guest speaker. Now, just to give you a heads up for, oh, actually, keep on going, Chris. When we come to this slide for the next meeting, I'll tell you what's happening there. So if you would like to join the RASC, we'd encourage you to do that. Regular membership is $88. Family is $82.50 plus $15 per adult, $810 per youth. And youth membership for those under 21 years of age is $53, or under 25 if they're a student. So what do you get with that membership? Well, locally, we have the 10 Bean Telescope Loan Library. Once we get back into the museum, we have the our library, the Stan Mott Library. And of course, we had the Fred Lawson Observatory out the other side of Elmont. And then nationally, you will receive the Sky News, which comes out every 2 months. The Journal comes out every 2 months. The Observer's Handbook comes out at the start of the year, an excellent resource. And monthly, we have our astronauts. Gordon Webster is our editor for that. He's always looking for articles. And some of our observations and some of the presentations are also in astronauts as well. So our next meeting is Friday, November the 5th. And at that meeting, Paul Cloninger will be our first speaker on narrowband images. And then we have Pavel Boudreau, who's going to be talking about time-lapse photography. So we have 2 speakers at our November 5th meeting. November 5th happens to be the new moon as well. And then just to look ahead to December the 3rd is our annual general meeting. And following the annual general meeting, I've arranged for Jeremy Kazub to talk about his self-contained Aurora camera that he has put together. So those are our talks coming up to the end of this year. So thank you folks for coming out tonight. And we'll see you in November. Hopefully we have some clear skies. Thanks. Have a good evening.